Okay, so the theorem. There's a very famous theorem, and probably you learned this in your high school. Binomial theorem. Binomial means polynomial with just two terms, like this, binomial. And this raised to the nth power. And there is a nice way to expand this. This is equal to k from 0 to n choose k, x to the k, y to the n minus k. So you can immediately expand this, and then you see the coefficient of this term is n choose k. And this is why this is called binomial coefficient, right? Binomial theorem. So it's the coefficient of this binomial power. Sorry, binomial coefficient. Okay, so how can you prove this? The proof is just to expand it. So when you expand this, so what is this? It's basically x plus y times x plus y times dot 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 x plus y. We have n polynomials multiplied all together. So how do we expand a product of polynomials? So product of two, what about product of two polynomials? We select, so when you expand like a plus b plus c times x plus y, something like that, you select one term in each factor, and then you multiply, right? Ax and plus, you select this and this, ay, etc. We select one term in each factor, and then we multiply the selected factors, selected terms, and that gives us one term in the expansion. That's how we expand product of polynomials. So here, select one term in each vector, right? For instance, like this term, I'm going to select this in the first vector, maybe this in the second vector, etc., etc., and then maybe this in the last vector. This is one way to select. Then this one term in the expansion. If you multiply them, that gives us one term. So for example, x plus y, product of two binomials. We select x, and that gives us x times x, right? And we can select x times y, or we can select y and x, or we can select y and y, like that. But as you can see, these are the same thing. xy equals yx because they commute. So in each expansion, in each term of the expansion, like this, let's call these are the terms in the expansion. Okay. We have this. Z1, so Z2, dot, 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 Zn. So let's Z1 is the term that we selected in the first vector. It can be either x or y. Z2 is the term that we selected from the second vector, etc. So every term in the expansion looks like this, like here. You can see everything is like that, where each xi is either x or y, right? But if you have this kind of thing, this will be, then this is always x to the something, y to the something. But because we have in total n letters, it must be x to the k times y to the n minus k for some k. Every factor looks like this, okay? And this may, so the terms with this value occurs, of course, more than once. So how many times do we have the terms equal to this? So number of terms, z1 dot 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 zn equal to this is what? this is just the arrangement of k-x's and n minus k-y's. This is equal to is the number of arrangements, all possible arrangements of k-x's like this and n minus k-y's. Just a binomial, it's like a binomial sequence. A binary sequence, right? Zeros and ones, given number of zeros, given number of ones. So we know this, which is n choose k, right? So this term occurs exactly this many times for every k from 0 to n. That means exactly this. The coefficient in this expansion, if you expand this, the coefficient of this is exactly n choose k. That's the proof. For every k, we just checked that the term in the expansion, number of terms expansion equal to this is exactly this. So this is a binomial theorem, and it has many interesting applications. So some of them, I'm going to tell you some of them. So corollary, there are interesting corollaries. By the way, here, let's say y equals 1. Still it's true, because it's true for every x and every y. I'm going to put y equals 1. Then we have like 1 plus x to the n equals summation k from 0 to n, and choose k, x to the k. We had before y to the n minus k, but y equals 1, so it's gone. So, and let's set also x equals 1. Then here, this is always 1. You can forget about this. Then here is the sum of the binomial coefficient. So n choose 0, n choose 1. I'm going to use this, expand this like without summation. The sum of all binomial coefficients with top number n is equal to x equals 1 here, 2 to the n. So it's 2 to the n. So the sum of the binomial sequence, binomial coefficients is a power of 2. And now, here, I said x equals 1. I said x equals minus 1 now. Let's say x equals minus 1. Then x to the k will be plus or minus 1 depending on the parity of k. And if you set x equals minus 1, this will be 0. So the 0, and here we have alternating sum, n0, n1, n2, minus etc. Right? Equals 0. Or equivalently, let's move all the negative terms to the other side. Then what this means is that sum of all binomial coefficients with even number at the bottom equals sum of all binomial coefficients with odd numbers at the bottom. So it continues until it reaches the n. Okay? It's fine. So, and also there's an interesting corollary. Here is an identity of a polynomial, right? So you can consider a derivative of this. So take the derivative. Differentiate both sides with respect to x. Then what happens here? We get, do you remember how to differentiate the polynomial? The chain rule here. So it's going to just n times 1 plus x to the n minus 1. Derivative of this is this with respect to x. And derivative of this with respect to x, we just take the derivative at each term, term by term. And derivative of this, we all know this k times x to the k minus 1. So is this. Okay? Very easy. And again, here I'm going to put x equals 1 over here. What happens is, here n times 2 to the n minus 1 equals summation k from 0 to n. This is 1, so k times n choose k. This is another interesting identity. Okay. These all came from the binomial theorem. All right. And there is another identity, also very famous. It's called Pascal's identity. So n choose k equals n choose k, n minus 1 choose k plus n minus 1 choose k minus 1. Proof. Probably the most straightforward way to prove this is to use the formula for this. We know the formula for this, so you can just use n factorial divided by k factorial minus k factorial. You just use it and then substitute there and then just compute, and you will prove that will prove it. But that's not very interesting, just the computation. So I'm going to give you more combinatorial proof by considering the meaning of each side. So what is n choose k? It has many combinatorial meanings. One of them is number of k subsets of an n element set. Or simply, let's say 1 up to n. Okay? It's the number of k subsets by definition. But we are going to divide these k subsets into two classes. So it is either number of k subsets, because every subset may or may not have element n, right? So number of k subsets of 1 dot 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 n containing n. Some subsets would contain these, but some subsets not. So, and number of k subsets of this not containing n, right? There are only two cases. Either it contains n or does not contain n. Of course, it's still the sum of this. Okay. So, what about the first one? This we need to select k elements from here, but n is already there. So we just assume that it is assumed that it's already there. Then among the remaining n minus 1 integers, we have to select k minus 1 elements to make k element subset. Okay? So the first one will be n minus 1 choose k minus 1. The second one, they don't have n. That means we just select integers from 1 up to n minus 1 because we know that n is not there. That is, of course, n minus 1. But now we have to choose the whole k integers. Is this. Of course, they're the same. So they have this kind of meaning. And this Pascal's identity, using this, we can create a triangular array of binomial coefficients, and it's called the Pascal triangle, and it has very nice property. The Pascal triangle. So it's a triangular array of binomial coefficients like this. So each row, it begins with 0th row, and in the ith row, we will list all binomial coefficients. I choose something. Okay, so like 1 choose 0, 1 choose 1 like that, and then 2 choose 0, 2 choose 1 in this way, and 3 choose 0, 3 choose 1, 3 choose 2, etc. Like this. Continue like this. Okay, and let's compute this. This is 1, but the thing is, something choose 0 is always 1. So these things are all 1s, right? So these are, if you compute these numbers, they will be 1, 1, 1, 1, etc. And this way also, maybe like 1, 1, 1, 1. These are all 1s. These are all 1s. Now we need to fill the inside part. So let me go further. So this thing can be obtained by adding the two numbers above it. Because here, if you have like n choose k, if you look at k nth row, and we have n choose k, and then here n minus 1 choose k minus 1, n minus 1 choose k, like this. So the binomial coefficients are arranged in this way. So the previous theorem, Pascal's identity, says this number is equal to the sum of these numbers, right? That means this part is equal to sum of this, so it's 2. And this thing is sum of these 2, the 3, this 3. This is sum of this, 4, 6, 4, 1, and then if you want, you can do one more. So 1, 5, 10, 10, 5, 1, etc. You can, in this way, you can complete this triangle very easily without using any formula, just using this Pascal's triangle. And if you look at this, there are interesting features of this triangle. For instance, what is the sum of the elements in each row? 1, 3, 3, 1 is 8, right? 2, 1, 2, 1 is 4. 1, 1, 2 is 1. This, if you're 16, 32, it goes like that. But we already know this because this is just the sum of the binomial coefficient, 3, 0, 3, 1, etc. That we know, we proved that it is equal to 2 to the 3, which is 8. So the sum of the integers in ith row of the Pascal triangle is 2 to the n. Another interesting thing is, there are many, but just a list. If you look at some number over here, this is the sum of things over here. 10 is equal to 6, 3, 1. Or 10 is equal to this. This plus this plus this plus this. 5 is equal to this plus this plus this plus this. Right? This is true in general. And I heard that some students said this is a hockey stick theorem, something, right? Have you heard of hockey stick theorem? Because it looks like a hockey stick, if you know. So the theorem is that can be written in this way: n plus 1 choose k plus 1 equals k choose k. K plus 1. This is equivalent to what I said, if you consider the arrangement of the numbers. And proof. You can prove this using induction. You should prove this by induction. First proof, induction. And I'm going to give you another proof. Second proof, direct proof. Because induction, you need computations, not very exciting. But for direct, we can consider we can understand both sides combinatorially, and then it will naturally explain this equation. So what is this? N plus 1, k plus 1. Of course, there are several ways of doing this. K plus 1 subsets of n plus 1 element, or number of k plus 1 tuples, I1 ... I k plus 1, as we did before. 1 I1 I k plus 1 less than or equal to n plus 1. Okay? Of course, yes, you can think of this as a subset. Subset are all these things, so you can list them in an increasing way. And then we will divide this into several classes according to the last element, the largest element. The largest element, integer, I k plus 1, can be what? K plus it cannot be smaller than this, right? Because we have already k integers smaller than this. So the smallest possible candidate for this will be k plus 1. And it can be k plus 2, can be one of this. What is the largest possible number for this? N plus 1. Okay. These are all possibilities for this. So suppose that this is fixed. Say fixed to be j. And of course j is k plus 1, n plus 1, between k plus 1 and n plus 1, like we saw over here. And then what is this? Number of tuples once this is given. The number of tuples ik and ik plus 1, where we have ik less than ik plus 1. But what is this? This is fixed j, right? So basically, then that means this is less than or equal to j minus 1, right? Because it's strictly less than j. We have j integers, and among them, we need to select k integers. So number of tuples like this, where, in which the last element is fixed to be j, this is equal to such tuples. We have j minus 1 integers, and among them we have to select k, like here. And because j can be any integer among these, it will be the sum. So that means this number is equal to sum over all j from k plus 1, n plus 1, j minus 1, k. We just divided this into several cases, and then we add them, then that's it. But you can see, if you expand this is exactly the same thing. K, choose k, you increase the top number like this, up to the last one, which is this. And that's the proof. There are many, many identities like this, involving binomial coefficient. And in most cases, we have nice combinatorial proofs like this. But sometimes you can, I think you can prove both, like using induction or computation, or you can prove combinatorially like this. You will see more examples in maybe homework and exercises. Okay, then I'll stop here. Thank you for your attention.